Hi guys, this video today is going to be a review of SOHCAHTOA and special right triangles. And these are concepts that you've learned before in geometry, so I think that you will remember a lot of them. So we're going to go through this part pretty quickly. This part, it might be a little bit of extension, so we'll go, I'll try to explain some things for sure, but I don't think it'll take too long. One thing is, if I have this triangle set up, go ahead and label yours 3 and then 4. What would this side be? Well, we know we would have to do Pythagorean theorem for that, or if you have it memorized, then you know it's 5. And they're called Pythagorean triples. The Pythagorean triples are good things to memorize because they will save you time on standardized tests, things like ACT, SAT, things like that. If you know if it's 3 and 4, then the other one's 5, and you don't have to do the Pythagorean theorem, it will save you some time. A bit of formatting, I don't know why, but they kept doubling up. And then I would fix it, and then I would double it up again. So I'm not sure how it shows up on yours, but on mine, just ignore those other sine, cosine, tangent. All right, so remember that sine is opposite over hypotenuse, cosine is adjacent over hypotenuse, tangent is opposite over adjacent, and that's where we get the phrase SOHCAHTOA from. So we're going to have to look at this and figure out what's what. Remember this theta? That's what that is a theta, and that is the variable that we often use for angles. So if we're talking about theta here, the sine is opposite over adjacent. That's 3 over 5. The cosine is adjacent over hypotenuse. That's going to be 4 over 5. And the tangent is opposite over adjacent. That's going to be 3 over 4. All right, so that's just a basic general review of SOHCAHTOA. Of course, there are a lot more things that we can do with it, but for now, I just want you to remember some of that information. Let's go down to the second part, which is special right triangles. And before we jump into here, let's just go back and remember some things from geometry. Do you remember how special right triangles worked in geometry? Let's say you have a 45, 45, 90. Let's say I know that this side is 1. Well, then how long is the other leg? Well, it's also 1, right? And then how long is the hypotenuse? The hypotenuse is going to be square root of 2. Now that should have been something that you memorized and used in geometry. And then you could kind of go back and forth. Like if this, whatever you know from this side, you would divide by radical 2 to find this side. So for instance, you don't have to draw this, but let's just do 2 examples maybe. Let's say this is a 45, 45, 90. If this is 5, how long is this side and how long is the hypotenuse? All right, you should know that this is a 5 and this is a 5 radical 2. What if it's not? This is a poorly drawn one. Let's say again this is a 45, 45, 90. What if this is a 7? How long is the other side? Well, think about it. To get from here to here, we multiplied by radical 2. So to go the other way, we divide by radical 2. So this would be 7 over radical 2. But of course, we don't leave a radical in the denominator, so our answer is 7 radical 2 over 2. That's going to be a side length if the hypotenuse is 7. If you want to write these down as examples, you can, but you don't need to. I'm going to erase them now. Okay, well, how about if it's a 30, 60, 90? Well, the easiest one in this situation is if this side is a 1, then how long are the other two? Well, if this side is a 1, then the hypotenuse is a 2, and the long leg is a radical 3. And so I always just remember 1, 2, radical 3, whereas this one is 1 to radical 2. And these proportions that I just drew, these ratios that I just drew, they're out of order of each other. I just think it's easier to think of 1, 2, 3, right? 1, 2, 3, and you just have to remember the radical 3 is the long leg, the 2 is the hypotenuse. The way I know that is because I know this is a half of a equilateral triangle. And so if this is 2, this would be 2, and this would be 2, so that's a 1. So that's a 1, that's a 2, that's a radical 3. Once again, you need to know these. They were things that you learned in geometry. We're going to be using them in this unit. Let me do a couple more review problems like I did a second ago. Okay, again, these 3 examples, if you want to draw them, you can, but you don't have to. Let's go through and think about how this would work. If this is a 5, how long are the other 2 sides? Given that all of these are 30, 60, 90s, okay? I didn't label them, but we're doing a quick example, 30, 60, 90. If this is 5, then this is 10, and this is 5 radical 3. Okay, what if the other way? What if we know what this is a 6? If we know this is a 6, this is half of that. and that's 3. And this side is radical 3 times as long, so it's 3 radical 3. Well, what if it's the 12 that we know? That is the long leg. What if it's the long leg that we know? Then what we have to do is this side, the short side, is going to be 12 divided by radical 3. This is going to take some simplifying. That's radical 3 down there. So 12 radical 3 over 3, that reduces down to 4 radical 3. So this side is 4 radical 3. If this side is 4 radical 3, how long is the hypotenuse? The hypotenuse is twice as long. That is 8 radical 3. In the assignment on the Delta Math, there are problems that are similar to this. So once again, if you want to write these down, go for it. If you don't want to, you don't need to. They're just kind of side examples. But all of that is background knowledge to what we actually do need to know for this unit, which is these little triangles that have a hypotenuse of 1. So we've been talking about the unit circle. And in that unit circle, this is a radius of 1, this is a radius of 1, this is a radius 1, this is a radius of 1. Well, also any other hypotenuse would be a 1, right? Each of those would be a 1. And anywhere you went in there would be a 1 for the hypotenuse. So what we are concerned about in this lesson is, what if the hypotenuse is 1, then how long are the other two sides? And so it's going to come back to these rules that we were just talking about a second ago. We said if we know the hypotenuse, we have to divide by radical 2 to get to the side. So if I know this hypotenuse, I have to divide by radical 2 to get to the other side. And of course, we never leave a radical in the denominator, so we have to multiply by radical 2 on the top and bottom. And so each of these sides is radical 2 over 2. Now, let me also show you a different way, because another way to do that is not by memorizing, but by using the Pythagorean Theorem. If we called this x and we called this x, we could do the Pythagorean Theorem. And so we would get x squared plus x squared equals 1 squared. So we would get x squared plus x squared is 2x squared. So now if I'm solving this for x, I'm going to divide by 2. So now I have x squared is 1/2. I square root both sides. And so I get the square root of 1/2. And that is radical 1 over radical 2, which is just 1 over radical 2, which is where I was a second ago. I multiply both sides by top and bottom by radical 2, and I get radical 2 over 2. So if you don't remember these rules, you can kind of go back to the Pythagorean Theorem. Won't work for you every single time, but it will work for you a lot of times. So each of these sides is radical 2 over 2. All right, so we had to do a little bit of remembering, a little bit of review to find out all that information. But now that we have it, if this is a 45-degree angle, then what's the sine of 45? Well, it's opposite over hypotenuse. So that is a radical 2 over 2 all over 1, which is really just radical 2 over 2. So the sine of 45 is radical 2 over 2. How about cosine? Cosine is adjacent over hypotenuse. Well, that's the exact same thing, right? So it's also radical 2 over 2. And the last one, how about the tangent of 45? The tangent of 45 is opposite over adjacent. That's radical 2 over 2 over radical 2 over 2. That's the same thing over itself. Anytime you have the same thing on top of itself, that equals 1. So the sine is radical 2 over 2, cosine also radical 2 over 2, tangent is 1. The reason we're doing these is we're going to put these onto our unit circle. And so these are going to be important numbers to remember in that unit circle. We're trying to put all the pieces of that unit circle together. All right, how about the 30, 60, 90? All right, remember that this is like it's a half of an equilateral. And so if it's a half of an equilateral, if this is 1, this side must be 1/2. And the long leg is radical 3 times as long as that one, the short leg. So the long leg is radical 3 over 2. Okay, so now we know our three sides. So now the sine of 30 is opposite over hypotenuse. That's 1/2 over 1, that's just 1/2. The cosine, radical 3 over 2 all over 1, adjacent over hypotenuse, that's radical 3 over 2. And the tangent is opposite over adjacent. Opposite over adjacent is 1/2 over radical 3 over 2. We studied rational functions in this class for a reason. We need to know how to use those and what to do with them. So we learned from that unit that these 2's cancel off. And so now we just have 1 over radical 3. Of course, we can't leave that radical in the denominator, so we come up with an answer of radical 3 over 3. So the tangent of 30 degrees is radical 3 over 3. Last triangle, it's the same triangle, right? It's just oriented differently. And so we don't have to go through that whole logic. We know that this is 1/2 and this is radical 3 over 2. All we're doing now is kind of rearranging our opposite and adjacent. So sine opposite over hypotenuse, cosine adjacent over hypotenuse, and tangent opposite over adjacent. And this time on the tangent, when we do our reducing, we don't actually need to do any radical business. It's just radical 3. Because it was radical 3 over 1, and that's just radical 3. Okay, like I said, the reason we're doing this is we are going to put these onto our unit circle and start learning more about the unit circle. Because on the unit circle, we filled in the degrees when we did that paper folding video, and you filled out the radians, but we haven't filled out the coordinates. That's where we're going next, is we're going to learn how to fill in these coordinates with those unit triangles that we were just taking a look at. The last thing here, there is a summary. We have learned a lot this week. Some of it's been review, but a lot of it's been new. Why don't you take a few minutes to summarize the 3 days of notes from this week?